Hello everybody, this is Miss Woods. Today I'm going to teach you about absolute entropy and entropy change. So first I want to start off by saying thank you for continuing to work hard for Miss Hanson and I. We both know it could be easy for you to be on the couch binge watching Netflix instead of doing AP Chemistry, but you're choosing to watch this video and work, so thank you so much. And also I hope that you're watching this video healthy and your family is healthy and that everybody is doing okay. Alright, so let's get started. So entropy, right? You learned all about entropy in the last video with this idea of disorder, right? And when there's more disorder, the entropy is higher, right? So entropy is represented, what in the world is that? So entropy, right, is represented by the letter S. Right, so absolute entropy represents the change in entropy when a substance is heated from absolute zero to a certain temperature. So absolute zero, right, if you're not sure what that is, maybe you've heard of it, you're just not sure of what it is though, that is the lowest theoretic temperature that can be reached. And that temperature is 0 Kelvin. Right, so I know that you guys aren't just going through your day saying, oh my gosh, it is a beautiful 280 Kelvin outside, it's great. Nobody thinks like that. So, but to put this 0 Kelvin into perspective for you, right, it's a negative 460 degrees Fahrenheit. Right, so extremely cold temperature. So, I have this image for you, right? And it's showing a substance changing from a solid to a liquid, and then a liquid to a gas. And you guys should know, hopefully, that in order for something to change phases, that you have to increase the temperature. But it's also important to remember that when you're increasing the temperature, you're also increasing the movement of a substance. So at 0 Kelvin, right, interesting enough, all movement stops. So all movement stops. Right, so everything is completely still at 0 Kelvin. So if scientists want to find the entropy of a substance, right, they will cool it down all the way to 0 Kelvin, right, and then slowly start increasing the temperature. Right, so as the temperature increases, that means the movement is increasing. Right, but remember, if the faster something is moving, the more disorder it's going to have, right? Which means that you're also increasing the entropy. Okay, so they can measure the entropy of a substance through calorimetry, right? Cooling something down, heating it up, and then ultimately calculating how much energy was absorbed from those temperature change, or from that temperature change. So let's move on down to our equation. All right, so if you take a look at this, hopefully this equation looks familiar to you, because this is the same equation that we used when we were calculating the standard change in enthalpy. So remember this little degree sign here, right? That is our representation of standard. Right, so just saying that these entropies were calculated or measured at standard conditions. So that is 1 atm, 273 Kelvin. Or if the substance is aqueous, that substance was 1 molar. Right, so just to get this idea that when these things are measured, everything will have the same conditions, right? So that is so those are variables that we can eliminate, right, to cause these changes. So we have this symbol here in the equation, right? That's sigma, so that means the sum, right? In math, sum means addition. So then we have NP and NR. right? If you think about it, what does N always represent in any equation that we've been using so far? Hopefully, moles came to mind, right? So NP is moles of product. And NR is moles of reactant. Okay, so let's put this equation to use. So there's an example for you. All right, example 1. It says sulfur dioxide oxidized in air to form sulfur trioxide, according to the equation below. Right, so part A just wants you to predict whether you think entropy increases or decreases. So why don't you go ahead and just make a prediction. After we do the calculation, I'll come back up and show you how to make the proper prediction, but just take a guess. If you need to pause the video in order to do that, please do so. Alright, so part B says calculate the change in standard entropy of the reaction using this information below. So it's important to note, right, that these values were collected the same way that I was explaining earlier, right? These substances were cooled down to 0 Kelvin and heated up to a certain temperature, and these values were measured using calorimetry, or calculated using calorimetry. So our equation, right, if I scroll back up for a second, right, I want to start with my products, right? So I want to know what the sum is when I multiply my moles of each product times their respected entropies. So if I come down here, whoops, hopefully I'm not giving you guys motion sickness, Lord. Alright, so I'm going to do change of our standard entropy of the reaction equals, so I'm going to start with my products again. So I have 2 moles of SO3. So I'm going to do, 2 moles times the entropy of SO3, which is 257. And that's joules per Kelvin times mole. Oh god, now I'm really going to give you guys motion sickness. Alright, times mole. Okay. So then, if I go back up, right, now, since I'm done with my products, I'm going to focus on my reactants, right? So I'm going to subtract what I get from my products, the moles of the reactant times their entropies. So let me scroll back down. Right, so I'm going to say minus, right, so minus, so I have 2 moles of SO2, so minus 2 moles, and then times SO2's entropy, which is 248. Right? And then I'm going to add that, because I have another reactant, right? So the sum of this, right, O2, I only have 1 mole of O2, so I just really have to say plus 205 joules per Kelvin times mole. Okay. So, now if I wanted to solve this out, right, I get maybe, right, so I get the change in the standard enthalpy of a reaction equals 514 minus, right, minus 701. Okay, so my change in the standard enthalpy of this reaction is a negative 187. Right, so our units this time, right, so I was multiplying our moles over this joules over Kelvin times moles, so those moles cancel out. So the unit that we're left with here is joules per Kelvin. right? So how much energy was absorbed or lost per Kelvin. So it's important to think about what in the world does this negative mean, right? So that's telling us that throughout this reaction, the entropy has decreased. Okay, so that means that it's less probable for SO3 to decompose to form SO2 and O2, right? So let me write that down for you. So it's less probable for SO3 to decompose to form SO2 and O2, right? And then when I say less probable, right, it's unfavorable. Right, meaning that it's not likely to happen, right? The forward reaction is much more favorable than the reverse reaction. So if we go back up to where you guys made a prediction, right, let me erase this part real quick so I can make more notes on here. So when we're trying to predict whether entropy increases or decreases, we focus on which substances are in the gas state, right? Because gases have the higher disorder, which means they have the highest entropy. So we could predict what happens to the entropy depending on what's happening with those gas substances. So in this reaction, right, every substance is a gas, which is nice. So we have to see about how does the amount of gas change over the reaction. So in the first reaction, right, I have 2 moles of SO2 and 1 mole of O2. So total I have 3 moles starting off, right, 3 moles of gas starting off. And then in the end, right, I am ending with 2 moles of gas. So it's fair to say that this reaction is becoming less or more ordered, right, as the reaction is taking place. So I can predict that this is going to be a negative change in entropy. Okay. So why don't you guys go ahead and try the second example on your own, and then you can press play on the video when you're ready to go over it. Alright, so let's see how you did on this problem. So first it says predict if the entropy increases or decreases. So I am going to focus on the substances that are gases. So again, in this reaction, every single substance is a gas. So I got to look at how the amount of gas changes from beginning to end. So in this one, right, I have 4 moles of NH3 and 5 moles of O2. So that means I have 9 moles of gaseous substances to start. And then I change that to 4 moles of NO and 6 moles of water. So that gives me 10 moles. Right, so the amount of gas increases this time. So as this reaction takes place, it becomes more disordered, which means I'm going to have a positive change in entropy. Right, so it's going to be an increase. So let's do the calculation to see if this prediction is correct. So same thing as last time, right? I'm going to use purple this time. I like purple. It's a nice color. So the change in, right, our standard entropy equals, right, so I'm going to start with my products again. So I have 4 moles of NO, right? And the entropy of NO is 211, so I'm going to multiply that 4 moles times 211 joules per Kelvin times moles. Okay. Plus, so this time I have two products, so I need to add those together. So plus 6 moles of water, and then the entropy of water is 189 joules per Kelvin times mole. Okay. So then I am, let me put another, if I can, right, another parenthesis there. So then I'm going to subtract my reactants now. So I have 4 moles of NH3, and the entropy of that is 193 joules per Kelvin times moles. All right, plus I have 5 moles of O2. So 5 moles times O2, so 205 is oxygen's entropy. So joules per Kelvin times mole. Okay, so if I solve this one all the way out now, let me give myself some more space. So we change the standard entropy of the reaction equals. So if I figure out the sum of my products, I get 1978. And remember, my moles cancel out here, so the units for that number are joules over Kelvin, right? And then minus the sum that I got for my reactants, which is 1797 joules per Kelvin. Okay, so the change in the standard entropy of this reaction, right, is going to be a positive 181 joules per Kelvin. All right, so our prediction above was correct. So now what does this mean, right? So what does this positive entropy mean? So this time our entropy increased. Right, so that means that it is more probable for NO and H2O to react together. So more probable for NO and H2O to react to form NH3 and O2. Okay, so remember, everything wants to be more disordered, right? More probability. So a reaction is more favorable to go in the direction of where more disorder can occur. All right, so this is favorable. Okay, so cool. That's our first set of calculations. All right, so sometimes you may be asked to calculate the standard entropy of one of the reactants or one of the products. So we use the exact same formula, right? But this time we're just solving for a different thing. So this time I have aluminum oxide being reduced by hydrogen to form aluminum solid and water. So this time it's asking me to calculate the entropy or the standard entropy of aluminum. So it gives me what the change in entropy is. So I can do 179 joules per Kelvin. Right, so that's going to equal, again, I'm starting off with my products. So I have 2 moles of aluminum. All right, so I'm going to say 2, but I don't know its entropy, right? That's what I'm trying to find. So I'm going to say 2x. All right, so plus, I have 3 moles of water, so 3 moles times water's entropy, which is 189 joules per Kelvin times moles. Okay, and then I can subtract now my reactants, so minus. All right, so I have only 1 mole of aluminum oxide. So I'm going to say minus, I don't have to do times 1 mole. I mean, if you really want to, you can, right, to help us understand what units are canceling out. So 1 mole times 51, right, and here's our units for that, plus, let's see, 3 moles of H2, right, and the entropy of, or the change in standard entropy of H2 is 131 joules moles. Okay, so now that we have our equation all filled out, we can start solving. So we got 179 joules per Kelvin equals 2x plus 567 joules per mole. Okay. So minus 444 joules per mole. Okay. So, oops, I'm sorry. Joules per Kelvin. Let me fix that on both of these. I'm sorry. Okay, so joules per Kelvin, right, minus 444 joules per Kelvin. Okay, so I can subtract over now I can add over the 444 to get a value of 623 joules per Kelvin. Right, and that gives me 2x plus 567 joules per Kelvin. Okay. So now I can subtract over the 567 to get x all alone, or to get x on the side by its own. So then you get 56 joules per Kelvin equals 2x. So it's important to remember that this 2 here is representing the moles, right? So when you divide that 2 back over, right, we're going to put moles back on the bottom to have x equal 28 joules per Kelvin times mole. Okay, so that is our standard entropy of aluminum. All right, so why don't you guys go ahead and pause the video and complete example 4, and then hit play when you're ready. All right, so last example of the day. You guys are doing great. So this time I have nickel 2 sulfide being oxidized to form nickel 2 oxide and sulfur dioxide. So in this one, it wants us to calculate the standard entropy of nickel 2 sulfide. Right, so this time my change in the standard entropy of the reaction is a negative value. So I'm going to do negative 149 joules per Kelvin. All right, and that equals, so again, starting with my products, I have 2 moles of SO2, so 2 moles, and I'll multiply that by its entropy, which is 248. Okay. And since I have 2 products, I have to add those together. Sorry, that's an ugly plus sign. All right, so plus 2 moles of the nickel 2 oxide. So 2 moles times 38 joules per Kelvin times moles. Okay, and I'm going to subtract that now from my reactants. So I have 2 moles of nickel 2 sulfide, so 2 moles, and the entropy of nickel 2 sulfide is unknown. So actually I'm just going to change this to be 2x, right, plus the 3 here, so 3 moles of O2, and its entropy is 205 joules per Kelvin times moles. Okay, so then when I start to solve this out, alright, I get negative 149 joules per Kelvin equals, let's see, 572 minus, right, minus our 2x plus 615 joules per mole. Let me actually erase this and put some units on my numbers here so it's easy to follow for you guys. Alright, so 572, why did the thickness change? Alright, so 572, oh my goodness. Let's see, hold on. That's ridiculous size. Let's see if that's better. Alright, so 572 joules per Kelvin. Alright. Minus our 2x plus 615 joules per Kelvin. Okay, so I can subtract over my 572 to get a negative 721 joules per Kelvin, right? And that equals, so our negative sign here kind of gets distributed to both of those values. So it's going to equal negative 2x minus 615 joules per Kelvin. Right, so I can add the 615 to both sides to give me a negative 106 joules per Kelvin. And that equals negative 2x. So I'm going to divide two negative numbers, which means it's going to turn into a positive value. Again, remember this 2 here is representing the amount of moles. Oops. All right. So this case, x is going to equal 53 joules per Kelvin times moles. Okay, so I hope you guys got that right. If you did, nice job. If you didn't, hopefully you see where you went wrong. So that is the end of the video teaching you about absolute entropy and entropy change. If you have any questions, please let Miss Hanson and I know. If not, I hope you guys have a great rest of your day.